Okay, I think we can more or less get started. So we're very pleased to have Gong-Bo Zhao, who is an expert in cosmology and I guess on galactic surveys. So he's going to tell us about cosmological implications of the eBOSS DR16 observations. So thank you very much.
Oh, thank you, Ian. It's a great pleasure to give this talk, and thanks for inviting me. So from this first slide, you can guess what I'm gonna talk about. You see these nice pictures from the Sloan collaboration. Basically, you see those BAO features on the right. Those are actual measurements. Those are actual fitting to the real data. So you see these curves, they have different colors because they are from different kind of tracers, and I will expand in this talk. I'm Gong-Bo Zhao from National Observatory in Beijing. Okay, so what is eBOSS? eBOSS is called the Extended Baryonic Acoustic Oscillation Survey. It's part of the Sloan 4 project. So you see from this illustration, we are sitting here on the right, present, we are here. Now we are looking back into the universe. So this is the CMB large-scale loss scattering surface at redshift 1100. Now, before eBOSS, there was another one called the BOSS, surveying the universe up to redshift 0.6. And there is a gap between redshift 0.6 and redshift 3, where we had Lyman alpha forest. So before eBOSS, there was a gap in the volume. Now, the main goal of eBOSS is to fill in this gap by probing the expansion and structural growth of the universe using different kinds of tracers. So in this sense, it is a multi-tracer survey of the large volume of the universe. The instrument we use is this plot on the right with the Sloan Digital Sky telescope. The aperture is 2.5 meter, installed on New Mexico in the US. So on July the 20th this year, there was an official release of the latest result. That is the final result of the Sloan cosmology program. So basically, we released the data we call data release 16, DR16, with more than 20 papers. So there is an interesting title in this press release, no need to mind the gap, because we have already filled in the gap. We fill in the gap, that gap is 11 billion years in expansion history, and that is really cool. If you want to know more, you can go to this website, it has more details. So I know there are lots of papers. I got some complaints from people that they kind of get lost from these papers. So I hope that my talk can serve as a guideline for you if you want to read those papers. Actually, those papers are classified in terms of tracers. For example, we have two papers for the emission line galaxies, one in K-space, one in the configuration space. We have two for the luminous red galaxies in the same way. And we have two for the cross correlations. We have two for the clustering quasars, one for the Lyman alpha BAL. And we have a big alphabetical paper summarizing this cosmological implications in this paper. And we also have several supporting papers for the mock catalogs and how to create the catalogs, how to do the target selection, etc. So again, let me present this figure. We are sitting here in the center. We look back in time. So let's start from this green dots. That is the Sloan 1, Sloan 2 program. That was mainly for nearby galaxies with a very shallow redshift. That program was run 1998 to 2008. Then followed by this, we started the BOSS in 2008 or 9. Then the main tracer for BOSS was the old red galaxies here in pink. We went up to redshift 0.6. Then beyond that, as I said, there is a gap between redshift 0.6 and redshift like 3, just below the lemma of a forest. That is the goal for the eBOSS. You see the difference between BOSS and eBOSS is that in eBOSS we had different tracers. We had very old red galaxies, the LRGs, and we also survey the young galaxies. Those are star-forming blue galaxies, also called emission line galaxies. And we also have quasars and also the lemma of a forest on top. So let me start from this concept. Why do we do this, and what kind of information can we get from those big surveys? When we do the massive redshift surveys, you can see this is illustration from the BOSS observations. Each dot here is a galaxy. Now, basically, we take a huge amount of data, then we study the clustering, the 3D clustering of this data set, and figure out what's expansion history and structural growth from this pattern. So the galaxy survey primarily has 3 pieces of key information. One is called baryonic acoustic oscillation. That is the standard ruler because of the physics in the early universe. That is the interaction between the photons and the baryons. And that results in a frozen scale about 150 megaparsec in co-moving distance. And that is very much affected by the nature of dark energy. So today, by measuring this clustering scale of the galaxies, we can infer the property of dark energy. So in short, BAO is related to the nature of dark energy at the background level. Another piece of information is redshift space distortions. We know the galaxies, they move not only because of the Hubble expansion of the universe, but also because of the peculiar motions, the local motions of the galaxies due to the gravitational potential. So because of that, the clustering of the galaxies is not isotropic. It is anisotropic due to this the peculiar motion. And because the peculiar motion is a result of gravitational potential, so that is a direct probe of the nature of gravity on cosmological scales. So RSD is related to gravity. So the main difference between BAO and RSD, in short, you can remember that BAO is at the background level, but RSD is at the perturbation level. If you go to a little smaller scales, if there are neutrinos free streaming in the universe, those neutrinos can destroy the gravitational potential formed by the dark matter and galaxies. So because the neutrinos, they have small mass and they have a large momentum. So that's why if we observe that small scales, there is a lack of power on the power spectrum. In other words, there is not as much clustering as on the large scales. That is a measurement of the neutrino mass, because neutrino mass can be translated to a damping scale on the power spectrum. So these 3 key pieces of information corresponds to these 3 big signs, and those are important topics in modern science, as we know. So what do we really measure? So given a telescope, then we target into a galaxy. So first we can measure 2 angles on the sky, theta and phi, or RA and DEC. Then the 3rd dimension is given by the redshift, like this, by taking a spectra of a galaxy, then compare this spectra to the spectra in the rest frame, then we can figure out how much it redshifted in the wavelength. So that is a measurement of redshift. And given these 3 coordinates, we can construct a map in redshift space. It is redshift space because we get a distance from the redshift. Now, again, in this eBOSS result, we have this measurement of the clustering using 4 different kinds of tracers, actually. The lemma of a forest, quasars, ELD, and LRDs. And observationally, this is just to give you a sense what does the raw data look like. For example, for the emission line galaxies, they start forming young galaxies. So they really, you can easily detect this kind of line. For example, this is O2. This is the primary line we are looking for. By using this O2, we can figure out how much redshift it has. And for the LRGs, there are more lines to use. And for the quasars, we can use magnesium or carbon 4 or carbon 3 to determine the redshift. This is the footprint of eBOSS for different tracers. You see the biggest area in purple, that is the LRG. So we observe LRGs actually twice. So for the first time, we surveyed LRG in a BOSS program, but those LRGs are primarily below redshift 0.6, but we had a little tail above redshift 0.6, a little bit, not much. So that is BOSS. Then in the eBOSS program, we continue to survey the LRGs beyond redshift 0.6. So in this DR16 analysis, we basically combine the LRGs observed in the redshift tail beyond redshift 0.6 in BOSS, and combine those with the new LRGs observed in eBOSS. That basically is the purple plus this pink area. And blue means the ELG. You see there is some overlap between the LRG and the ELG. Basically 100% of the ELG, they overlap with the LRG, but only like 10% of the LRG, they overlap with the ELG. That is an interesting fact. I will focus later on because we can study the cross correlation between these different two tracers. That will give us additional information. And this is quasars in yellow. So basically they have almost the same footprint as the eBOSS LRG, because the eBOSS LRG and the quasars, they are observed simultaneously. Okay, so this is I'll show you the clustering analysis tracer by tracer, starting from the LRGs. So the LRGs covers the redshift 0.6 to 1.0 with effective redshift like 0.77. We've taken the area about 9,500 square degree. We've taken.
Can I ask how you get an effective redshift? What is the process by which that happens?
Oh, you mean how did we take the redshift?
Determine what the effective redshift is.
Oh, okay. Right, so that's a good question. So actually, in actual measurement, what we meant like this power spectrum or correlation function, that is actually the redshift weighted two-point correlation function, because each pair, they have different redshift. To determine this effective redshift, we basically compute the redshift for each pair. We run the pair counts in our catalog. Then we sum over, so for each pair, we use the redshift in the middle between these two pairs, that's the average. Then we take this average of all the pairs in the volume. That is then we get the effective redshift.
So it's essentially a very crude measurement, right?
Well, yeah, in some sense. Because on linear scale, all the power spectrum at different redshifts, they have the same shape. So you can compress all this power spectrum, the pairs, into one effective redshift. But this is not true on nonlinear scales. They have different shape. So it's impossible to compress. And there are higher order terms. By using a single redshift, effective redshift, you throw away the higher order terms. That's the assumption. There are better ways, like performing the redshift, optimal redshift weights. We don't use any effective redshift. Instead, we just take the integral of all the pairs along the line of sight. Then we do the same for the modeling. In that way, we don't have to assume any effective redshifts. Yeah. So this is the visual in visualization of the LRG, you see a nice BAO ring with this RSD pattern, and we detect a clear BAO signal from the correlation functions, and also the RSD in the multiples. And this is the K-space analysis. You see this very nice Vigo, and also the RSD. Then we combine the measurement in a K-space and S-space into a final consensus measurement. We take into account the correlation coefficients properly. That is from the MOX. Then this is the final results. You see the Planck lambda CDM model is within 1 sigma. That's basically consistent with Planck measurement. So far LRG is okay. It's fine. It's perfectly fine. But the ELD, well, as you can see from this plot, actually the collaboration spent a lot of time on the ELD to understand the clustering of the ELD, because that is the first time that we use the emission line galaxy as a tracer for the clustering. BLD covers a little deeper redshifts with a larger effective redshifts, but we only have like 700 square degree as a footprint, and we don't have much spectra of the LDs, only 170,000. So you see from this 2-point correlation function, the BAO peak is not very significant. Actually, we believe that there is a significant systematics from the observations, because it is really difficult to do the analysis with the ELGs. One fact is that not all the ELGs are in the halos. And then when we run the target selection, there are some uncertainties. And also when we do the target selection using the imaging data. So those imaging data is basically a combination of decals and dark energy survey. And then those two samples, they don't have exactly the same depth in terms of imaging. So that could be propagated into the measurement of the clustering in the final sample. That's why you see a big scatter in the correlation function, and also in the power spectrum, the BAO vehicles are not very significant. That is also probably because. Yes?
Can I ask, you actually fitted the model to the data there, or I mean, does a straight line just not work? I mean, this data looks more or less consistent with a straight line. Nothing to see here, right?
Yeah, there is a little significance, but basically, in terms of the significance for the BAO, it's just about 1 sigma. It's not a straight line, but it's not very significant.
So nothing to see. Sigma is nothing to see, right? More or less.
Yeah, more or less.
For particles.
So in terms of the BAO, I mean, for the BAO, I mean, before the BAO reconstruction, the signal is really low. But after the reconstruction, it helps a lot. We can have the 2 sigma detection of the BAO after the post-reconstruction. So as I said, because of this observation of systematics, that is primarily due to the photometry and also the redshift failures, we have to do something different from the LRGs to mitigate this observational angular systematics. That is a layer of complexities. In practice, what we did was to basically throw away some clustering in angular wedges. We basically run a shuffling of the REN deck to remove some part of the data. That is, for example, if we made a silly mistake in a photometry, that will affect the angular clustering. We don't want that to happen, so we just shuffle our randoms. We basically take exactly the same REN deck for the random as the data. So basically, we applied the integral constraint of the angular clustering that can remove partially the angular systematics. We test this on the mobs, and it works very well. So we believe that in the final measurement, we significantly reduced this kind of systematics. I will come back to this. I know this is a bit confusing. I will come back to this. So yeah, that's the ELG. And also we measured RSD from the ELG. As you can read from this figure, the F-sigma rate from the ELG sample is pretty low compared to the LRG at the similar redshifts. The F-sigma rate is like 0.45 something, but here is only 0.3. It's very low. We believe this is not due to systematics. We believe this is real. Then we need DESI to confirm this. And quasar is okay. We have enough number of quasars. We have the density is not very high, so we couldn't run the BAL reconstruction on the quasars. But we had a decent measurement of the BAL and RSD from the quasars. You see this nice wiggle. But interestingly, the F-sigma rate from the quasars is much higher than the Planck prediction. It's 1 sigma higher. Maybe that's signals interesting new physics here. Right, so coming back to this LRG and ELG, they overlap very much in footprint. So the overlapping area is like 700 square degree, red and blue. And they have a decent overlap in redshift as well. So by LRG, I mean this CMAS LRG plus eBOSS LRG. So this pink plus red, and blue is the ELG. So they overlap between 0.6 and 1.0. So then we ask a question, why not we just cross-correlate the two? Because by cross-correlating, we can take the advantage that we can sort of cancel out the cosmic variance on large scales. The reason is this: if you have only one tracer, so that your overdensity field traces the dark matter density field with some stochastic noise, the short noise. However, you measure this, you are subject to cosmic variance because there is a random Gaussian field here, delta. We have a number of pairs, very few pairs on large scales. That's the source of cosmic variance. But if you have two tracers or even more tracers, then you can make a direct comparison between these two, between delta G1 and delta G2. If the epsilon are very small, then you can take the ratio between these two delta fields, and that will cancel out the dark matter over density field. So in this sense, this ratio, you can measure this ratio by infinite precision because there is no Gaussian random field. And this ratio, from this ratio, you can figure out beta, which is the RSD parameter. This nice idea was proposed in these two papers. And another advantage of running this is that by cross-correlating the systematics, they will not correlate because the LRG and ELG, they have different photometry. They were observed differently. So by looking at the cross power, it's cleaner signal, basically. It's immune to the angular systematics. So we performed the analysis in these two papers in this overlapping area. Let me go to a little details. So this is the estimator we used for the measurement of the power spectrum. Basically, it's the Yamamoto estimator. We just make use of the FFTW to speed up the calculation. And all these are basically normal way to compute the power spectrum multiples. And one generalization, however, is that here, because we want to measure the cross power, then we have to, like for tracer A and tracer B, we have to add these additional terms in this estimator. so that the measurement for tracer A and tracer B are symmetric. That's the only addition to the estimator. And there is a bit of complexity in the modeling, because the modeling we use is not just a simple linear Kaiser model plus damping term. It's the quasi-nonlinear model in the redshift space, which is the TNS model. In that model, there are correction terms, like this A and B correction terms. Now we have to recalculate those terms for the cross power. That is highly non-trivial. Basically, we extend this model to the cross correlation properly, include all these corrections in the modeling. Another effect to consider is the Alcock-Paczynski effect. We know if in a real space, if there's no RSD at all, so the 3D correlation function should be isotropic, because if there's no RSD, it should be isotropic. But then remember, we convert the redshift to distance using a cosmology. If you get that cosmology wrong, then you can distort your distance along the line of sight and across line of sight differently. And that will result in anisotropy in the 3D, even without the RSD. That is called AP effect. And that effect actually can be used in the modeling to infer we call dilation parameter alpha perp and alpha parallel. That is the direct measurement of H and dA, respectively. So we put that into our modeling. Right, so let me go to this systematics again, which is the big headache for the ELD sample. As I said, we did some sort of non-trivial thing in the configuration space to mitigate this, to remove basically some angular clustering. And in the K-space, things can be very different. So in my paper, I proposed a new method, which is very simple. It's basically algebra, but that works very well. Suppose there is some unknown systematics coupled to the transverse mode. That is the toy model. In the actual case, it could be a non-local function. But at the first order, we assume that this unknown angular systematics is pure angular. So it only couples to mu equals 0 mode, that is transverse mode. Then from this, you can take the random polynomial decomposition of this. Then you can get this first, PL in this way. Then you can calculate the next order in the expansion, that's PL plus 2. That by comparing these two, you can just take naive subtraction. You can cancel out this unknown systematics, the X of K, with this coefficient AL in this form. So in terms of QL, then from this you can see that the QL observed is actually the QL true in the data. The X is basically removed by this algebra. I am showing this in the illustration here. So to test this, we create mocks with this angular contaminations. Then we measure this normal PL, the power spectrum, from the ELD mocks. So this red, yellow, red, and gray, they are multiple, portable, and stackable. Then we take a difference between the mocks with systematics and the mocks without systematics. So if there's no issue, you should see a 0 in all the panels. But in terms of PL, for example, in the cells, you don't see this. You see there is offset in terms of delta L on large scales. That is angular systematics. But then when we do the same measurement in terms of QL, everything go back to 0 nicely. that basically validates our simple prescription for this angular systematics. But you may ask that the information content in the PL is different from that in the QL, because in QL, basically that is a difference between different orders of PL that has a lot less information than in the PL. For example, if you measure Q0, Q2, Q4, you can never revert this equation to figure out P0, P2, and P4. So you lose information. The solution to this is that, for example, I just measure a QL, a Q for my LRD, Q for my ELD. But then to supplement, I can measure the cross power between P LRD and P ELD. I don't have to do the Qs for the cross power, because in the cross power there is no angular systematics, because the angular photometry they don't correlate. So I just simply use P, and given the P from the cross power, and I can solve for P0, P2, and P4. So that is the trick we use to get information back from this cross power. So in this sense, the cross power is indeed very useful for both statistical and systematic settings. But this is the measurement in P in terms of P and Q for the LRG, ELG, and cross correlation. So you can see by eye that in the ELG, there are some outliers, like the glitches, that might be a signal of the systematics. So different color are for P0, P4, and P2. But then in terms of the cross power, although cross power has large error, but you see it's more consistent. Sorry, the data points are real data from the eBOSS sample, and the band is from the MOG catalog with systematics. You see the consistency between the MOG and data is better in terms of the cross power, and it is actually better in terms of Q. And this is the SGC. Right, so this is the 2D clustering from the cross power alone. You see there's a cross power. And from this cross power, you see the RSD signal very well. So that's the elongation along the long line of sight. So we basically detect RSD by 4 sigma from this cross power alone. I believe that is the first measurement of F sigma 8 from the cross power in the sample. That is pretty interesting. In the end, we got the final measurement in these 2 big data points in red. This is BAL distance, and this is the F sigma 8. In comparison with other measurements like the quasars and the Planck, and also the eBOSS measurements here. You see this data points, F sigma 8, is very low at redshift 0.845. Well, as I said, it could be some residual systematics, unknown systematics there, or it could be a signal of like modified gravity or something we need further investigation. Also, in terms of BAL, there is some offset compared to the Planck 18. So this is a consistency check between my measurement and the single tracer measurement in Hector's paper and also in Arnold's paper. This is for the LRG and this is for the ELG. So we got very nice measurement consistency with each other, although we use different methods to mitigate the systematics. So, right, so here is a little cosmology implications of our measurement. So we just combine all the BAL data with the eBOSS BAL. Then we just try to constrain omega lambda and omega matter by using all the BAL today. And we got a tight measurement on this omega lambda parameter. So basically, omega lambda equals 0 model is excluded by 11 sigma now by the BAL data alone. That is a good, a nice independent evidence of the cosmic acceleration. And a little bit more on dark energy study. So in 2017, we reconstructed the W of Z of dark energy from the eBOSS data. And we sort of saw a 3.5 sigma signal of this evolution. And 2018, we reconstructed the density, not just the W, but the energy density of dark energy. We also see some interesting features. As you can see, at high redshifts, the dark energy density can even go to negative. I know this is hard to understand, but for example, in terms of modified gravity, this can be explained. This energy density isn't real, but it's an effective energy density from the modification of gravity. And for the latest measurement, we haven't done this. We are doing this, but we just naively compare our measurement with our old reconstruction in terms of dA and H. They are consistent within sigma, but you can see that, for example, in terms of H, the new data will drag this down a little bit more, making it more deviate from lambda CDM. We are working on this. Hopefully, we can finish this soon. And this is the constraint on W parameters in a parameterization form. So basically, this W not WA is just a linear parameterization of W in terms of the scale factor. In this alphabetical paper, you see by using everything, together, Planck, Sloan, and other data, there is sort of 1 sigma deviation from lambda CDM, even in this simple parameterization. That might be due to the tension between different data sets. As people know that we heard the tension very much these days. So maybe the tension can result in some non-trivial behavior of dark energy. And another key science driver of eBOSS is the neutrino mass. In order to distinguish between these 2 mass hierarchies of neutrinos, we have to measure this neutrino mass to a very good precision. For example, to rule out the inverted hierarchy. So the 2 sigma, I think this 2 sigma upper limit of neutrino mass should be like 0.06 eV. But today we are not there yet. Combining everything together, so that the upper limit is like 0.1 to the best. Hopefully, with DESI, we can go there. We can just distinguish between these 2 scenarios. Right. So this is the hypertension. We just hear day and days. Let me start from this, I think. Right, this is the H0 measurement from the local Cepheids and supernovae, the distance ladder. And we know BAO alone cannot measure H0. What it really measures is H0 times RD. RD is the sound horizon at the recombination. So you can see BAO alone gives you this band. Then to determine H0, you need some prior on either omega B, like this BBN prior, will give you a small H0. Then if you combine this BAO with local measurement, of course, you get a large H0. Then CMB gives you a very small H0. So that is the hypertension problem. Then in this upper plot, I'm showing this measurement of H0 from BAO. I just separately use the BAO below redshift 1 and above redshift 1 in combination of the BBN parameter. As you can see, you can get a different, very different constraint in red and in gray, depending on what kind of BAO you want to use. For the low Z BAO, you can get a smaller H0, but a high Z BAO gives you a higher H0. That might be seem like an internal inconsistency, or maybe some extended cosmology there to be explored. But then when you combine everything together, you get this small blue contour, which is still away from the local measurement by more than 2 sigma.
So can I ask a couple of questions about this plot?
Yeah.
So the first thing is, why would you choose z equals 1?
Well, yeah. So beyond z equal 1 is basically quasar and Lyman alpha forest. And also redshift 1 is sort of a point where dark energy can become important. I guess there is no good reason why it has to be exactly 1. We just want to, yeah.
You could be 0.8, right, or 0.8, and you'd still get this feature, right?
Yeah. Sure.
Now, as well, your degeneracy between H0 and omega m seems to flip when you go from greater than 1 to z less than 1. Do you understand what's going on there? And it
That's
seems
right.
like lambda
Yeah.
CDM.
Yeah, that's because of the different z dependence of omega matter and dark energy. At low redshift, dark energy, I mean, is important. So in the Friedmann equation, you can see this omega matter 1 plus z to the cubed and plus 1 minus omega matter. Then at different redshifts, the degeneracy between these two, it is different.
No, but now I'm very confused by your plot, because my expectation is as matter density goes down, H0 goes up. I mean, the claims were that there was a local underdensity that would basically cause a small rise in H0. So, but that's high redshift BAO. Okay.
Yeah.
So this is the usual degeneracy I would expect at low redshift. Am I misinterpreting this plot?
So I think at very high redshift, you can ignore dark energy. It's basically pure matter. What
gray does look like, so your gray contours are essentially high Z, right?
Yeah.
Okay.
So what you measure is small omega matter times h squared.
No, that's fine. So basically what I'm saying here is the usual degeneracy I expect at low redshift is omega m goes down and H0 goes up.
You mean it has to be the red?
That would be the red in your plot. Is it
I'm
possible?
pretty sure we didn't get it wrong. It just, I mean, this curve should rotate using different redshifts. Do you agree?
Okay.
Then with different redshifts, it kind of give you a different degeneracy.
Okay, because cosmic chronometers give you exactly the same degeneracy, right? Virtually.
H of Z, yeah.
Any data I've seen at low Z, it's this gray degeneracy.
Yeah.
Okay, thanks.
Perhaps the CB prior can make some difference, because we measure, there is a RD and RD is evolved here.
Okay. This is in one of your papers. Is it one of the SDSS papers?
Yeah, this is alphabetical paper. This big long paper.
Oh, the big long one. Okay, thanks.
Yeah, so you see the tension in terms of sigma 8 is getting better, but it's still not perfectly consistent with Planck. Then this is by SDSS, I mean, we combine everything together in Sloan, including Sloan 1, 2, and BOSS and eBOSS. In the end, as you see, this Planck is still far away from distance ladder, and the Sloan blue contour is away from this distance ladder. But to remember that everything should depend on the prior. How do you treat the RD? And either by BBM prior or some other prior, because you really can't measure H0 on its own. And I want to mention that there is interesting study by Ryan and Arman. It's going to appear as an eBOSS paper that is on this topic, model-independent reconstruction of the expansion history. I think they will address the problem here on RD and H0. Basically, you measure H0 times RD, not them separately. And this is the measurement of modified gravity theories. So in principle, you can parameterize modified gravity using this mu and sigma functions as a function of A, and also it could be a function of K as well. So in this paper, we just explored a simplest extension to lambda CDM. We parameterized mu and sigma in this one as the Planck did. We didn't see any deviation from GR. GR is here 0, 0. So everything is very consistent. But earlier, last year, we did another study. We parameterized this mu and basically the same thing, eta or sigma, using a non-parametric form. And we've seen something unusual like this the data points. And we did correlate the data points using PCA. We sort of see 3 sigma deviation from GR. Of course, we will run this with the new data and quantify the Bayesian evidence, anything like that, to quantify the real significance of this modified gravity. I think this is my last slide summarizing the progress we've made since the beginning of Sloan. So stage 2 is really a very old time that time we didn't have any Sloan. So that's the stage 2. I think we used WMAP for this. Then orange is the stage 2 plus Sloan. That's orange. You see there's a big improvement. For example, on the neutrino mass and the sigma rate. Now, green is stage 3, that is Planck without Sloan. So if you compare green with orange, you see orange is actually better than green in some cases, like omega matter and neutrino mass. So they're similar. For example, neutrino mass, the omega matter. That means even you can go from WMAP to Planck, the things can be worse without Sloan. Now, Sloan is very important. Combining Sloan with WMAP can be better than Planck alone. Now this is stage 3. I think that's with everything so far. Yeah. I think I will stop here. Basically, I want to say we finished the survey successfully. We've done the multi-tracer exercise. That is, we want to get ready for DESI when we can do a much better multi-trace analysis. And the cross power is indeed very useful. And so far, the lambda CDM seems to be okay, but there are other possibilities which cannot be ruled out at the moment. Thank you very much.
Okay, so thank you very much for the very interesting talk. I guess we're open for questions and comments. Any questions or comments online? This mic is on. I think you can use that.
So, may I ask some question?
Yeah.
Can you go to the former slide that shows the W of Z reconstruction? Yeah, super. So yeah, so but actually I'm a little confused that so what's the reason do you think it's do you think cause the deviation from the mass 1 in the hybrid shift for the W of Z? Yeah.
At that time, that was because of the lemma alpha forest. That is very off from the Planck. So
yeah, so I understand. So But actually, we have already know that the lambda alpha deviates from the plot. So so we think that this is not surprising, right? We expect that if we include the lambda alpha in the hybrid shifts, we will have some deviations from the number set model.
Yeah.
I think it's not surprising.
Yeah, that's the main reason why this is low. And also that is not only just lambda alpha, and also this OHD, H of Z measurement. But everything combined, it sort of favors.
But actually, OHD, I think they are consistent with the number set model.
Well, consistent in if you fit a lambda CDM, it could be consistent because of the huge error bar. But then if you give it more degrees of freedom, it can change the shape. And that shape is consistent with lambda alpha forest.
Okay. Yeah. So in this plot, you show that if we reconstruct W of Z, there may be some deviation. But have you ever considered the interaction between data region and data matter?
That's a good question. So basically, at the background level, so this W can be translated into a interaction between dark matter and dark energy in a naive way. But at the perturbation level, it could be different. We tried this before in a 2015 paper, but we didn't try this on the latest data.
Okay. So I expect that if you for example, if you fit W of Z to be -1 and then you reconstruct the interaction between data and data matter, I think there may also some deviations from this data sets.
Yeah, exactly. There's one-to-one mapping between W and alpha. That's basically the interaction parameter there.
Yeah. Okay, thank you.
Hello, Gong-Bo. Can you hear me? Thanks for the talk. So I actually have two questions. So the first is, have you looked at the clustering? You obviously have, and just in the North Galactic Plane and the South Galactic Plane data separately, and do you see any difference?
Yeah, we tried this in the mocks and also in the data. The main difference is seen for the ELD sample. For the ELD, in the North, it's very bad, actually.
Okay.
In the ELG in the North, there is almost no peak, no BAO peak. It's highly contaminated by the systematics.
Okay. Do you see this? Do you see any difference in the LRGs?
No, in LRG it's pretty consistent.
Okay. So have you done the entire analysis? So you've gone through and calculated cosmological parameters just for the North Galactic Plane data and the South Galactic Plane separately?
I'm not sure. Perhaps in the LRG paper, Hector did this. Please check his paper. I think he did a careful analysis with North and South separately. But in the ELG, we didn't do North alone. We always do South alone, South plus North, because North is really bad.
So you don't use the North data?
No, we don't use the North alone.
Okay. I always find there's the difference in clustering in the North and South data, even for the DR12. So I was just curious.
Yeah, so in DR12, there is a difference in amplitude because of the, so that's why we use separate bias for North and South. That is because of the observing conditions are slightly different in North and South.
Okay.
So it's marginalized over the bias to account.
Okay, so you should use the data separately.
Yeah.
Is that also true for the these LRGs?
Yeah. So there's a slight difference. We always use separate bias, separate window function, separate parameters for the North and South.
Okay. Okay, thanks.
They share the same BAO parameter.
Yeah. Okay, thanks. The other thing is to what extent is the DR16 data public?
It's all public now. Now we are thinking how to release the mocks. They're pretty heavy. We are going to release this power spectrum measurement window function covariance matrix very soon.
Okay, but is the angular selection function public?
Angular selection, yeah, I don't think so, but we will make it public at some point so that people can reproduce everything we did.
Yeah, okay, that's great. Thanks.
Thanks.
Hi, Gong-Bo. Thanks for your talk. I just have one basic question. So in your cross power spectrum, is it necessary to consider the Zhao noise?
Yeah, we subtract off the Zhao noise in all these plots.
Even in the cross power spectrum?
No, so in the cross power, in the measurement, there is no Zhao noise.
There's no Zhao noise.
We don't have so this is a little bit confusing. So the cross power, it does have Zhao noise, of course, but in the measurement, you don't have to subtract off the Zhao noise. That because in the estimator, there is no Zhao noise.
Okay. Another question, can you go to the slides, the constraint from the cross power spectrum? Maybe the next one. Yeah.
Yeah.
Yes, this one. I can see the results. The two red dots from the cross power spectrum. I just wonder, do you have a comparison with the auto power spectrum and same redshift?
Oh no, sorry. So these red points are for the combined auto and cross, everything combined.
Everything combined.
Yeah.
Okay.
From the cross alone, we cannot measure BAL. We don't have that signal to noise. We can only measure APCTP.
Yeah. Okay. Okay.
And Armin, you've got a question?
Okay, I think my hand is raised, so I give myself this chance to talk. So Gong-Bo, can you explain a little bit about those BBN constraints which are used? I think this is a question for many people. That what are they and how model independent they are?
Yeah, so basically this is a flat weak prior on omega B H squared. So I think in the paper we want to be very conservative. I don't think BBN prior is dependent on late time in cosmology. It's sort of independent, conservative prior. I don't remember the exact number, but it's a wide prior on omega B H squared.
But the physics of the early universe cannot affect that. I mean, if you have, for example, let's say early dark energy, and that practically affects the expansion history and the ratio of the baryons and dark matter. So this constraint would be still robust against that, or this is based on this assumption that we have a reasonably, normal early universe?
Yeah, I think this is a very good question. If you have like early dark energy or some magnetic field in early universe, you will have a different BBN constraint. Definitely. So this BBN is a standard BBN, I think, normal early time physics. Yeah. So for the magnetic fielding, for example, you will change this quite a lot. You will have a different RD.
Right, yeah. Thank you.
Cheers.
Okay, any more questions or comments? It looks like maybe not. That may be the last question. So if not, then I guess we can thank our speaker again for a very interesting and comprehensive review of eBOSS results. Okay, thank you, Gong-Bo.
Oh, thank you very much. Thank you.